Welcome to the video introducing the chapter on chemical reactivity and mechanisms. We're going to start with talking about enthalpy. Remember, enthalpy is the heat of the reaction. So it is the energy that is exchanged between the reaction and its surroundings. Remember that bond breaking requires the system to absorb energy. So to break a bond, you have to put energy in. And that comes from our molecular orbital description, where the atomic orbitals are higher in energy than the bonding molecular orbital. So that means that energy is given off when you make a bond and energy is put in when you break a bond. So bonds can be broken in two ways. They can be broken homolytically, which means that we have one electron that goes in each direction. We have not learned this type of reaction yet. That is called a radical reaction. Over on the right, the heterolytic bond cleavage is the one that we're familiar with, where both electrons in the bond go in one direction. That's called a polar reaction. So this is polar and this is radical. In the next couple slides, we will be giving you values for bond breaking and bond making, and those are actually from the homolytic bond cleavage. But we'll go ahead and use those to estimate even for our polar reactions. Here's a table of bond dissociation energy values associated with each of these bonds being broken or formed. The values in the table are all positive, which means that these values in this table are associated with the bond breaking. And we will use this table a little later in our practice example. Remember, in an exothermic reaction, the energy is given off. So that means that the energy that is given off by bonds being formed exceeds the energy that needs to be put into the system to break bonds. In this case, the products are more stable. In an endothermic reaction, remember, energy is taken in. So this just means that the energy needed to be put into the system for bonds to be broken exceeds that of the energy that is given off by bonds being formed. And in this case, the products are less stable. So if we look at the energy diagrams for an exothermic versus an endothermic reaction, we can see that the exothermic reaction, the products are lower in energy than the starting materials. Energy is released because these products are more stable, so energy is given off into the surroundings. Delta H is negative, and the temperature of the surroundings increase. If we look at endothermic reactions, it's the opposite. Our products are higher in energy than our starting materials. That means energy had to have been consumed. Energy needs to be put into the system to raise those products to a higher energy. Delta H is positive in this situation, and the temperature of the surroundings decreases. This is an energy diagram, and it's a typical representation of a chemical reaction. So in these energy diagrams, we have to think about the x-axis. The x-axis is the reaction coordinate, or time. That's as the reaction proceeds forward. And the y-axis is enthalpy, and that's the energy. When we're calculating delta H for any given reaction, we're going to use the bond dissociation energies from that table. And we're going to look and see if this reaction is endothermic or exothermic. Remember, exothermic is going to have a negative delta H, and endothermic is going to have a positive delta H. So if we look at this reaction right here, we have propane reacted with Br2, where we add a Br to the center carbon right here, and then we end up with HBr as a side product. When we're doing these calculations, we're always going to want to do broken minus formed. So we're going to take all of the bonds that are broken, and we're going to subtract from it all of the energies associated with the bonds being formed. Broken minus formed. So if I look up at my reaction and see what bonds are broken, we do have a CH bond, right? So this did have an H on it, and that bond is going to be broken. And we also have a Br-Br bond. So the Br here, that bond is broken. And so we have a CH bond being broken and a Br-Br bond being broken. And so then we're going to go ahead and use the table to look these values up. This value is 397, and this value is 193 kilojoules per mole. If we look at what bonds are formed, we see that this bond is formed right here, and this bond is formed. So we have a CBr bond and an HBr bond being formed. And so right here we have CBr and then HBr. And so again, you look up those values, and it's 285 and 368 kilojoules per mole, respectively. So then we take the broken minus formed. And so here is our broken, which is this value plus this value. So we add those two together. And so we take the two values of the things that are being broken and add that up. And we take the two values that are being formed, we add that up. So if we add 397 plus 193, we end up getting 590. So that is our bonds broken. And then we subtract from it our bonds formed, keeping the values positive in the addition, but remember we are subtracting it. So that is where we get our negative sign. So we do the positive 285 plus 368, and we end up with 653. And when we do that math, we end up with negative 63 kilojoules per mole. Delta H is negative, so our reaction is exothermic. So if we move on to the second topic today, we'll talk about entropy, or delta S. Both enthalpy, delta H, and entropy, delta S, have to be considered when we're trying to decide whether or not a reaction will occur. Entropy can be described as molecular disorder, randomness, or freedom. It's usually the number of vibrational, rotational, or translational states of energy that a compound is distributed. So with entropy, when there are more moles of product than a reactant, we end up with a higher entropy. When a cyclic compound becomes acyclic, we will have higher delta S. And so here's where we pull it all together. Delta G of a reaction, or Gibbs free energy. The value of delta G involves both a term that involves enthalpy, or delta H, and a term that involves entropy, delta S. And the equation is delta G equals delta H minus T delta S, where T is the temperature of the reaction. In this class, we will not have to do any specific calculations for Gibbs free energy. We will, however, have to calculate delta H. So here's another example of calculating delta H for a reaction. Here's our reaction right here, and we have to decide whether it's endothermic or exothermic, and we have to calculate the value of delta H. And so let's first talk about what bonds are broken, because remember, we're going to use broken minus formed. So what bonds are broken here? We have a CH3 Cl bond that's broken, right, because it's replaced with the OH, and we have an H O bond broken right here because it becomes HCl. And so we have a CH3Cl bond broken, and we have an HOH bond broken. And then if we talk about what bonds are formed, we have a CH3OH bond formed right there, and we have an HCl bond formed. So if we do our broken minus formed, the bonds broken are going to be CH3Cl and the H2O. If we look those values up on the table, we have a CH3Cl bond broken. And I think this may be one of the hardest parts, is finding these values. CH3Cl, so we have 351. And then we have an H2O, so an HO bond broken. And that value is right here. So we're going to use 351 and 498 for our bonds broken, and that's right here. And then if we look at our bonds formed, we have a CH3OH bond formed, and that's 381. And we also have an HCl bond formed, and that's right here. And so we have 431. And so now from the table, we've gotten all the values we need to do the calculation. And so then we take broken, so we add these two values up, 849. And then if we add the bonds formed, that value is 812. And then if we take our broken minus our formed, we end up with positive 37 kilojoules per mole. And because that value is positive, it is endothermic. It turns out our answer is C, 37 kilojoules per mole, endothermic. This is a great start to this chapter. We did delta H, delta S, and a little bit of delta G. Okay, good luck.